So, yeah, as Viral said, I'm with Intel's Parallel Computing Lab, and we've been together with, Jeff, Keno, and all the core Julia developers. We've been working on trying to add threads into core Julia for quite a while now, and this is sort of a report out on where it stands. So, the conferences I'm used to going to, we always see foils like this. So I haven't seen this here yet, but this is sort of why we care, right? So this is 40 years of trend data. It's recently updated by Carl Rupp at Argonne. And this kind of makes it pretty clear that, while transistors are still scaling, the frequency is kind of flattened out over there. And single thread performance is still going up, but it's not going up really that fast anymore. Whereas the core counts over here, as you can see, are kind of jumping pretty rapidly. 2 years ago, dual core. Today, Haswell has 18 cores. So we have all these cores, and we have to, get to use them. So. So this is essentially it. Why threads? How are different programming languages done stuff with threads? How we've actually implemented parallelism, shared memory parallelism for Julia. A little discussion of the performance considerations in doing stuff like this, right? And then a kind of analysis of what the performance of what we've added and how well this stuff scales, right? So I should mention up front that my lab mostly focuses on HPC stuff, and all of this has sort of an HPC kind of bias to it. So you may see stuff missing or not entirely fitting with the kind of code you want to write right now, but that's my mea culpa for that kind of, right? So the hybrid model coming up, a lot of history, a lot of MPI-only codes out there are still slowly migrating to using a shared memory model, shared memory parallelism model, as well as MPI. And the standard protocol is to have a process per uniform memory access domain and threads within that. Why do we want to have any shared memory parallelism? It's bad, right? Bugs, it's Heisenbugs and so forth. Well, many-core is here, right? Especially in HPC, we have 60-plus cores, 70-plus cores around the corner. We're no longer talking a few threads, we're talking hundreds of threads. And your memory per core is actually shrinking all the time, and it is getting more and more impractical to start a process on each core and still have a significant amount of data on that node. And yeah, so hence shared memory parallelism. Also, and so MPI is also moving in this direction. MPI also has shared memory stuff being added to it as we speak, MPI 4. This is sort of debatable, and many people argue about this, but you can get better performance with threads than you can get with separate address-based processes. But of course, as we all know, this is prone to programmer error. So I'm not going to discuss why threads anymore. It becomes can be a religious argument, and that's not terribly useful. So dividing work among threads, you have a whole bunch of threads, right? How are you gonna use them? So this is sort of a one way of looking at forms of parallelism, right? There are others, of course, but this is one way to break it down. And task parallelism is what you see in lots of server-type applications or applications that run on one or two machines, where you have different threads running different codes, different pieces of code, different thread functions, and they're all interacting with each other through some form of queues, semaphores, whatever. This clearly doesn't scale very naturally, right? This in particular is where it's very, very hard to figure out whether you've caught every race condition between all your threads, because you have to reason about all thread interleavings between different pieces of code. The other kind, data parallelism, is essentially, all your threads are running the same code and they're just operating on different parts of data. And this is typically what HPC codes like to do, need to do, right? So Michael Scott over at Rochester has written a book and has done a little survey on how different programming languages have exposed threads to people. And these are the 6 principal ways. Now, there are, again, many perspectives on this, but this is historical. So dating back to Ada Algol 68, there are different forms of how you would program threads, how you would use them from the language. I won't read that out over there, but I guess I should point out that the 2 that we are mostly concerned with is parallel loops and fork join. Right, those are also the modern ones. RPCs also count, but we saw a bunch of stuff about that in the last talk. So another perspective over here about how you perceive parallel programs, right? So Arch up there, together with Mike McCool and James Reinders, wrote a book. This is a different book, Structured Parallel Programming, Patterns for Efficient Communication. And here the claim is sort of that all parallel programming can be fitted into one of a number of different patterns. And there's actually ongoing research in this space, algorithmic skeletons, they're called. And you know, that's not exactly what this talk is about. And there are, of course, other perspectives on how you should view the world of parallel programming. This is just sort of to give you a flavor of the models and ideas out over there in this space. Right? So what we have done with Julia is kind of the most basic, simple thing out there. It is data parallelism, parallel loops, essentially. A little bit more than that, but that's kind of clear over here. It's parallel loops, parallel blocks, begin-end blocks, and parallel calls. Right? So this is sort of that little code snippet up over there is how it works. Now, having seen how everybody's been using iJulia, I probably should have done something like that and had demos and done this on the fly, but didn't do that. You can try out all this stuff. All of this stuff is in a threading branch on GitHub for Julia, and we are actively working on merging it into master, which is tentatively scheduled for sometime this year, Q3, let's say. Okay, so there's a very contrived tiny example over here, computing the roots of quadratics. And that is sort of a toy example, but it does demonstrate that you just put the prefix that threads macro. All refers to an abstraction where you can partition the threads on your machine into different groups, and there's an all group is the default. And then you have your parallel loop. And this essentially statically partitions the iteration space of that parallel loop and distributes it among the threads and sticks an implicit barrier at the end, right? So the other forms are up there on the top right, right? So the for loop you saw in that, and this is the blocks, parallel blocks, and this is the call format, right? They all use the same thing internally, but this is what it's been applied to in terms of Julia constructs right now. So this is some of the behavior over here is controlled by environment variables, right? So you can you can tell Julia that you own this machine and nobody else is running stuff on it, and you do that setting Julia exclusive to 1. And what that will do is that will affinitize the thread starting from the first core and kind of lay out all the threads contiguously on the machine. That's pretty important, and I'll talk about why in a second. How many threads should Julia start? That's controlled by the num threads over here. And a lot of the time in programs or when you're doing stuff interactively, you don't need all the threads spinning and waiting for work, burning power. So there's a threshold after which they will essentially go to sleep. These are the only parameters that there are right now, and the defaults are adjustable. So how does this all actually work? How do those forms work, right? So this is sort of overviewing it over here. The entire interface essentially is a C function inside, inside Julia called JL threading run, right? And that takes 3 parameters. A Julia function that is the function that should be run by all the threads, a tuple of any arguments which are passed to that function, and as of right now, a reduction function which essentially is applied to the return values of these functions from all the threads, and the reduced value is returned from JL threading run, right? Or it will. The commits for reduction are sort of in the pipeline, right? So that's essentially what happens. The master thread, thread 1, is running along and sees an add threads macro, which translates down to this call. And it broadcasts these parameters, the function and so forth, to all the threads. And all the threads call the function and so on, right? That's the repetitive cycle over here. This is sort of to distinguish between the interface and how it's implemented, because the interface really is about parallel loops, and how it's done under the hood can change and may change going forward. But from a programming perspective, you're just saying, hey, this loop is parallel, the iterations are independent, go ahead and do it, right? So, right, so this is sort of, some of this is kind of basic parallel programming stuff, and some of it is a little bit more subtle than that, and it could end up being a pretty long discussion, though I do have time. These are different considerations for performance when you're parallelizing stuff. When you have an HPC code, it tends to follow a pattern of some serial code, a parallel block, some serial code, parallel block, and so on. And in those serial parts, you're doing MPI stuff, exchanges of data, and so forth, other things, right? Sometimes those parallel blocks are pretty short, right? But they are repeated a million times, right? So the whole process of broadcasting something to all your threads it's pretty important that you do that really fast and don't spend a whole bunch of time on that, right? This is especially true when you're talking about the new many-core processors, when one thread has to notify 200 plus threads of the work that needs to be done, right? So broadcast time is relevant. Barrier time, of course, is relevant. Task granularity. So this is actually kind of a very long discussion again. So very briefly, how fine-grained your tasks are when you are parallelizing some code is kind of pretty critical when it comes to how those tasks are distributed among threads. Static partitioning of tasks, even if the tasks are roughly of the same size, can still end up with so those orange parts of the bar over there are supposed to indicate when that thread finished all its assigned tasks and has nothing else to do. It kind of sits around waiting, and that's load imbalance, right? And load imbalance can typically be pretty bad, a very big time consumer in your parallel programs, more than you'd expect. And sometimes dynamic scheduling is the answer, but often it is not, right? So enough parallelism, of course, is a function. So you have this trade-off between what is the granularity of your task size and the amount of load. If your task sizes are too big, then you could end up with largish load imbalance. And if they're very small, then it can add other sorts of overhead, especially if you're doing dynamic scheduling. So the number of threads is an important consideration over here, and this actually relates into a second problem that I'll talk about later: nested parallelism or composability. And in general, in HPC, we don't oversubscribe cores whatsoever, because context switch overhead will kill your performance. You generally do not want to multiplex threads on top of cores. You just start one thread per hardware core and work with that, right? Failing that, stuff like, I mean, when I'm talking about, broadcasts and I'm talking about barriers and I'm saying that this is relevant, actually relevant in terms of overall application performance because they happen so frequently. Well, if you have some threads sleeping and all those threads have to wake up, the kernel has to context switch over to wake them up before they can start doing their parts, then not a whole lot is going to get done. So how do you multiplex stuff on top of limited number of threads, especially when you're nesting parallelism? But I'll talk about that later. So yeah, I already talked about that. So another consideration then is affinity, thread affinities and the implications on the cache. A typical pattern, again, in HPC codes is, for instance, PDE solvers do a kind of a stencil over a grid, right? So the grid is pretty regular often. For most types of HPC codes, they prefer to do regular stuff because it's a lot easier to scale that kind of thing. You will repeatedly run a stencil over that grid, many iterations, many time steps until stuff converges or so forth. And parts of that grid, right? When you partition the work across a bunch of threads, parts of that grid is loaded into the cache for each of those cores, the L1 cache, the LLC, so forth. So it would be kind of nice if the next time you did an iteration over there, that thread could hit in the cache, and it's not a different thread that's suddenly processing that part of the grid. This can again have a remarkable impact on performance because if you hit in the cache, you're talking a few cycles to do your operation, and if you have to, if you miss in the cache, then you're talking hundreds of cycles. And so the regular distribution of work is kind of important. Static scheduling is a pretty nice thing to have. So these are considerations that have sort of driven why we did, why the parallel functionality is the way it is right now. Right, nesting parallelism. So yeah, so this is kind of a real problem, a very serious problem, not entirely solved. Not at all solved. So suppose I've got beautiful multi-threaded Julia now. I'm writing a parallel loop, right? But inside my parallel loop, I'm going to call some BLAS function, right? Some beautifully optimized open BLAS or MKL function, right? And that is parallel in itself, and it's very carefully tuned. It's like optimized for different processor architectures. It's carefully all this cache behavior is managed, but I've already got all my threads running on the outside. So if each of those threads calls into a library and each of those spawns a whole bunch of other threads, then you get quadratic oversubscription right away, and your performance is really terrible, right? How do you fix this? You fix this essentially by turning off threading in the library. So all that effort that a whole bunch of people have put in to make those libraries performant and scale nicely, you're essentially turning all that off. Right, so yeah, so that's essentially what this is saying. Your scalability is limited to your outermost loop. Right, so how do we solve this problem in a better way than essentially turning off parallelism in libraries? Right, so work stealing is believed to be a significantly more composable kind of a way. I'm not sure everybody knows what work stealing is, so there's a little kind of very high-level review of what it does. And the idea here is that you don't have all your threads sitting and listening for a broadcast from thread 1, but each thread has a little deck, right? And when a thread's deck is empty, it randomly picks a victim thread and tries to steal from the back of it, right? So this is sort of very roughly how work stealing works, and you may have heard of Silk, and that's essentially what Silk came out of MIT originally, right? So that's essentially what Silk does. So what happens in this case, right? If you call a multi-threaded function from a parallel loop that's implemented on work stealing. you get parallelism when there's available parallelism, but the fact ends up being that when you spawn work, which is essentially what happens when you have a parallel loop inside a parallel loop, which is calling into a parallel library, all that stuff goes into the bottom of the queue for the thread, right? And so it cannot really be stolen by other threads until the outermost loop is complete, right? Can we talk after? You want to jump in, Arch?
I guess the server work executes serially until a processor becomes idle and available. And
Right.
At that point, the work forks. So you get breadth first. As long as there are idle resources, execution is breadth first.
Right, right. But if you have an outer parallel loop, then there are no idle resources until every thread has at least finished its allocation, right?
Yeah, when it finishes its own part of the loop, then it'll go off and become a thief.
Right, right. But what it can steal is from the back of the deck, right? Which is the outermost parallel loop.
Right. You get the efficiency, you get the full use of the processor.
Yeah, what you don't get is you don't get the efficiency of the highly optimized libraries because for the most part you still serialize all the way down, right? But okay, so there's a discussion to be had over here. But the point I'm trying to make over here is I don't believe that this is not really a solved problem. This is a problem with MKL. This is a problem with OpenBLAS. This is a problem with OpenMP, perhaps. And if everybody used Silk, maybe it isn't. But I think we need something a little bit better, right? And we don't have it yet. The composability problem is still a problem. Okay, so where are we at? Okay, so that's essentially the threading functionality that's there inside Julia right now. It's pretty basic, but it works pretty well. And to verify that it works, actually does work well, we did a bunch of analysis using it by writing a bunch of workloads that are multi-threaded. Yeah.
I may have missed it, but you're looking at data parallelism,
Mm-hmm.
and you have a shared data model.
Mm-hmm.
Was there anything in the Julia code that explicitly said this should be, oh, I'm thinking of different processes, different threads all have access to the same memory?
Right. Right. So we ported some HPC-like kernels, mostly written in MATLAB. We ported them to Julia. We added threads to them. We did a whole bunch of analysis on that. And to talk about that, did you plug in yet? Yeah. So Ranjan here interned with Intel Labs over the last few months, and he is at this point the newest employee of Julia Computing, right? So I'll have him talk through some of this stuff and come back. Is that working?
How do I turn this on? Is it green? No.
Hey everybody, can you hear me? Yeah, my name is Ranjan, and I'm from this university called Pamnany in India, the city of Hyderabad. I was interning with Intel for about 6 months, where I wrote this mix of HPC-like workloads. So we followed a certain methodology. We took MATLAB kernels that were generally available around the internet, and we ported them to Julia. We also did a rigorous performance comparison with MATLAB. So the MATLAB parallel computing toolbox allows you to do a couple of things. It has this feature called par4, which essentially allows you to speed up your loops, at least in theory, or at least it's supposed to. And then there's GPU acceleration with GPU arrays, which essentially declares all your data structures on the GPU memory and allows you to use the magic of the GPU. So yes, just for one workload, we have a performance comparison with C as well. So this is a summary of the results which we have. There are 3 workloads which we have right now, and 2 which have preliminary results. One is the 3D Laplace workload. Another workload is a simple Monte Carlo workload, and third is LBM stands for Lattice Boltzmann model. So essentially, the first column represents MATLAB, just firing up normal MATLAB. The second column represents MATLAB with GPU acceleration, which is usually the best performing MATLAB. And then we have single-threaded Julia, and then Julia with our threading infrastructure. So in most cases, we're able to sort of match or beat MATLAB with GPU. So we're able to do that with, on all the workloads. Sorry. So this is essentially a summary of our performance. So I'll just go into each one of these in a little more detail. So first is our 3D Laplace equation solver, which essentially solves your delta squared u equals 0. It's a well-known PDE and performs a 7-point stencil. This becomes bandwidth bound upon reaching a certain number of threads, as we shall soon see. I was wondering if you guys can see this graph. So essentially, the MATLAB code performs very badly. So what we did was we compared MATLAB code, which you just fire up generally like that, along with MATLAB, which runs just on a single computational thread. And some of the other workloads, the results are kind of surprising. But over here, every single version seems to perform badly. And so the general rule of thumb in MATLAB is to write vectorized statements, right? So this of course is a pretty bad idea because it generally uses a lot of memory. And so what we did was we devectorized all of that. And we sort of tested performance on both MATLAB and MATLAB with single threads. And when we ran this workload, it just didn't complete. I mean, we waited for like 15 minutes and just whatever. So and PAR4 usually always makes things worse. So again, I'm sorry, I don't mean to. I mean to. So it's pretty awful actually. So but GPU acceleration is actually kind of efficient. So we are able to see dramatic speedups on MATLAB GPU, but as we can see in some cases, it's not always going to work for you because you need to arrange your data structures in such a way. You need to throw in a bunch of rep maths and et cetera, integrates rep maths, and make sure that your memory access pattern is sort of as contiguous as possible, in keeping with the general GPU rules. So we were able to blow GPU out of the water with Julia threading, and in fact even the single threaded performance is a lot better than GPU. So take that, MATLAB. So we were able to get great scaling results. As you can see, it's almost as comparable to Ninja C. Let's move on to the next workload. Then we wrote a very simple Monte Carlo workload and most of the computers essentially within this one loop, which is embarrassingly parallel. And we saw, embarrassingly parallel stuff. Let's throw threads at it and see what happens. So we sort of ran around 1 million iterations. All these codes are available online also. So over here, so the first thing you notice here is finally MATLAB did manage to run. So here it takes about 35 seconds. And then we ran MATLAB with a single thread. And it performs a little worse. So here's the thing, MATLAB does a lot of parallelization under the hood, and essentially gives you that speed up with vectorized statements, which is why it's always desirable to write vectorized statements in MATLAB. And as you can see, you get a little bit of speed up there, around 7 seconds. So what happens when you what happens when you devectorize both of them and run MATLAB single, MATLAB normal, and MATLAB single? So here you go. The performance is very, very comparable. So which sort of tells you about how MATLAB actually parallelizes under the hood, and how this parallelization is not there when you're when it's devectorized essentially. So and then PAR4 comes along and then screws things up. So and then after that, we basically use GPU. So essentially, we had the separate data structure for the two assets which we were simulating, and we just made them GPU arrays. And this seemed to work pretty well. It worked really well, and for the most part, or not for the most part, in some cases it will work very well. And it reduces the performance to about 2.96 seconds. And that of course beats Julia on single thread. But we're able to sort of match performance with Julia threading. And we're able to achieve very good scaling results, as you can see. So the third workload is a lattice Boltzmann workload. It's basically modeling your fluid as a bunch of particles. And there are three key steps to it. There's a propagate step in which the particle sort of takes on the properties of its neighboring particles. And there's an equilibrium calculation step where you calculate this equilibrium distribution, and then a relaxation step where you say the nu is basically some combination of this equilibrium and this propagation. The code again is available online. So the most interesting part here is MATLAB single performs better than MATLAB, just normal MATLAB. But then who runs MATLAB single? So a lot of people may miss this actually. So I mean, this just goes to show you that some of MATLAB's parallelization, which it does under the hood, can work against it. And because of MATLAB's closed nature, it sort of works against itself. And again, when you devectorize MATLAB and run it, you can see there's a considerable performance difference. So there's a bunch of there's a bunch of vectorized statements in there which when you start running with loops, I believe that we devectorize even a small part of it. It literally through performance. So again, par4 we just couldn't get it to work. It kept finding dependencies where there were none. So there's some serious issues there. And MATLAB GPU. So what we did was we essentially took our key data structures, just made them deep GPU arrays. Essentially make everything GPU arrays. That's what MATLAB tells you to do. That's what we did, but it doesn't work. Performance again goes for a toss. So there are a lot of subtleties here which you must consider while using GPU, right? So again, Julia threading was very easily able to beat this. Right, so there are two other workloads which are currently in preliminary phase, so for which we have preliminary results. There's a 2D wave equation solver which uses a Chebyshev spectral method via FFT in space and a 2D finite difference in time. So this is actually a piece of code from the MATLAB website where they've arranged everything beautifully with all these rep maths and all that stuff. So this is actually used to demonstrate GPU acceleration, so they've arranged everything beautifully. So it's going to perform very well, just how they want it to, like so. 1.8 seconds on GPU, and even then you can see here, MATLAB running on single-threaded computation is outperforming normal MATLAB, which you would start up. Julia threading. Julia threading over here is actually what we've done is we've just taken FFT and FFTW and we've sort of tweaked the number of threads and improved performance here. So this again is a little bit of a work in progress. So the last workload is this topology optimization workload. So essentially you have this sort of grid and you're trying to find the most. So there's this load at this corner, right? And you're trying to find the best shape to sort of support this load. And this is called a shape optimization problem. And most of the compute is in this one finite element kernel, which is written in naive MATLAB, again found online. So over here, again, single-threaded performance beats MATLAB. Normal MATLAB. And as you can see, when you devectorize MATLAB, there is a huge difference. Also, Also, generally, remember I just told you that devectorized MATLAB should perform about the same way on normal MATLAB and MATLAB running on single thread, because it's essentially devectorized and that parallelism under the hood isn't there. So we've essentially just devectorized the main compute kernel, which is why you see the little difference here. If there are a bunch of other vectorized statements which we could have devectorized and got this bar back where it should be. Essentially, but this code was sort of like naively written, and it didn't assemble your sparse matrix in a very optimal way, like how Viral told us about a bad way of assembling a sparse matrix and what is a good way. It was using the bad way. So we put the good way in there, and we saw performance improvements. And then Julia with the new GC just beat everything. So yeah, thank you, Oscar. So yeah, so that's what we have from the workload side. Thank you, Kiran.
So just to wrap up, we've got a bunch of these workloads, but we would really like you guys to try this stuff out, right? Now, threading is not bulletproof. As you know, there's all sorts of gotchas, particularly in the runtime. So you will see seg faults. Please open issues, right? It's not so terribly alpha that it's unusable, as you can see. There's a lot of scaling that is there to be had, but it is clearly an in-development feature. Yeah, so take your Science workload or whatever other workload that you think can benefit from data parallelism, and try this stuff out and tell us, right, what we could do better and where it's broken. We found, of course, to kind of summarize over here that looking at our comparison with C, we can scale as well as OpenMP does, right? One of the things we learned over here is that if you're going to do GC in any high-level language, you're going to do automatic memory management, you better do it well, right? We found so the threading branch is old. It's not forked from current Julia master, and Julia, it's essentially forked from before the new generational GC went in. And so we can see, in some of these workloads, GC has consumed up to 40% of the entire runtime, right? So this top-up thing you can see over here, these are both single-threaded, but there's the difference in performance for the new GC and the old GC. So it can make a big difference, and making the new GC thread safe is, again, work in progress. We expect that many-core is going to make this even more problematic, because many-core makes everything parallel problematic. The whole question of parallel collection is sort of an unsolved problem. So it'd be pretty interesting to see how we'll deal with the memory management issue going forward. So coming soon, right? There's some very big open questions over here. I'll just leave that up over there and ask for questions.
Questions about just the hardware. I wasn't very familiar with it, so I was trying to look it up and just understand what motivated picking the NVIDIA Tesla K80 and then this was it 18-core Haswell chip.
Right.
Could you just kind of comment on, like, for someone who doesn't know much of the hardware, like, how do those things compare in price and capability?
So I wouldn't be able to tell you about price, but Tesla is the HPC part NVIDIA makes. K80 is the top-of-the-line HPC part. It's basically two K40s rammed in together. This, as far as I know, that is still the current fastest NVIDIA accelerator designed for HPC for double precision floating point. Haswell, this is the Xeon part that goes into current servers, and so we're just using the newest one out there. So yeah, as far as performance comparisons are concerned, we see performance comparisons with NVIDIA all the time, so we thought it would be kind of nice to turn it around.
Yeah.
I saw links on the slides to the original code. Is that the code that was ported into Julia?
Yes.
Was there a link in there to the Julia code, or where would we see the
No, there wasn't any Julia version when we started out. We just translated them.
Right.
Yeah.
So is that open source, your Julia version?
Yeah, some of it's on
So
the threading.
all three of these workloads are on the threading branch in test perf threads. Should have mentioned.
About how people should get the threading, how to get threading.
Yeah, I should have put that stuff up. The whole iJulia thing would have been pretty nice to have over here, but sorry.
Last question, just a point of information, if that's the 2880 cores, it's a 1.4 teraflops. But just for slide I couldn't read, you have 10 times faster on 18 cores or 10 times faster, or 18 threads or 10 threads, I couldn't read it.
It was 18 threads.
So 10 times faster on 18 threads, so.
Right, right. You don't get perfect scaling.
Yeah,
It's-
yeah, okay.
So, okay, out of time.
Take the questions later.
Yeah, please find me outside. I would really love to talk to more people about parallelism and how you could use it. Thanks a lot.
Anyone who wants to use multi-threading should check out the multi-threading branch, is that right?
It's just called threading.
It's just called threading, sorry. Threading and then make. All right, let's thank the speakers.